So we're now going on, and we're on this page right here, and we were talking about the characteristics of a neutron. We defined it by its origin, essentially its energy level, its production time. This is super important. When we talked about its production time, it was called a prompt versus a delayed neutron. We're going to find out that delayed neutrons represent a very small fraction of neutrons in the core. And that represents also a number. The fraction of delayed neutrons, fraction of neutrons, I'm going to put a little d here, neutrons delayed, the delayed neutrons, the fraction of delayed neutrons in the core is super important. We call that the beta of the core. Beta of the core. And it changes. So it's a small fraction, but it's a key, a very important fraction. So let's say I had at the beginning of core life versus end of core life. I'm going to take 10,000 neutrons out of the core. I'm just going to reach in and grab a representative sample of neutrons out of the core. Well, at the beginning of core life, the fraction of delayed neutrons versus prompt is really odd. Here's the prompt, and here's the delayed. Prompt neutrons represent 9,900 and about 30. Out of every 10,000, 9,930 are prompt. That's 99.3%. Delayed, there's only 70 or so out of every 10,000. That's an amazing number because remember, these prompt neutrons were born within 10 to the minus 14th seconds. These delayed neutrons were born on average 12.7 seconds. We don't have a control system that can control something occurring this fast, but we can definitely control these delayed neutrons. And these delayed neutrons are what are going to make our reactor self-controlling. Another thing, this shifts over core life. From the beginning of core life to the end of core life, if I was to reach in at the end of core life and get a representative sample, well, I'd have more prompt neutrons. That's a 30, by the way. Let me make that a little better. At the end of core life, I would have 9,950 prompt neutrons. And the delayed now would only be 50 neutrons. So the fraction of delayed neutrons over core life is going down from beginning to end of core life, and I'm getting more prompt neutrons. The beta of the core is going down from BOC, beginning of core life, to end of core life. Over core life, the fraction of delayed neutrons is going down. What that means is our reactor is getting very responsive. It's getting skittish. We are starting at the beginning of core life with a certain level of slow neutrons, and not slow, my bad, delayed neutrons, and at the end of core life we have less. That means the reactor is going to be much more responsive. This is going to be so key when we do reactor kinetics in topic number 3, this fraction of delayed neutrons. So what that ends up being then is prompt at BOC, we said, represented out of every 10,000, 9,930, and delayed represented 70 out of every 10,000. So what this is then is, if I was to put it in a percentage point form, it would be that, or 99.3% are prompt. Delayed would be this, 70 10,000ths, or 0.7%. And that changes over core life, that changes. At the end of core life in red, this changes to 9,950, which means prompt represent a larger percentage of the overall neutron population. 99.5% are prompt, and only 50 out of every 10,000, or 50 10,000ths. Or, another way of saying it, 0.5% are delayed. This is called the beta of the core, and the beta of the core is going down over core life because the delayed neutron fraction is going down over core life. Well, you got to ask yourself why. Why is beta of the core going down from BOC to EOC? Well, what's happening to the core? Let's look at it. BOC, what did the core consist of? It consists of what I put in it. So I put uranium-235 and I put uranium-238. However, at the end of core life, since we were trying to maximize transmutation, if you recall, that was turning uranium-238 into plutonium-239. At the end of core life, well, I have very little uranium-235. It's gone down. I have about the same uranium-238 minus whatever I've turned into plutonium-239. And each one of these has its own delayed neutron fraction. Each isotope has its own delayed neutron fraction. That is the beta of uranium-235. There's a beta of this isotope, uranium-238. There's a beta and a beta. And then there's also a beta for 239, which just means what is the probability that each one of these isotopes gives off a neutron in a delayed fashion. And when you put them all together, this equals the beta of the core. And when at the beginning of core life, I put them all together, the betas, the delayed neutron fraction of these, was the beta of that core. And you should draw this conclusion. Plutonium-239 doesn't give off as much neutrons in the form of delayed neutrons as uranium-235 does. Plutonium-239 tends to give off neutrons in a more prompt fashion. Prompt, which skews the beta of the core down. The delayed neutron fraction is going down, and the prompt neutron fraction is going up. Very key. Now let's look at a decay chain that actually creates these delayed neutrons. Here I have a neutron coming in, interacting with uranium-235. A fission event occurs. We know that we get a fission fragment, generally 2, sometimes 3 occurs. We know that what these are was dependent upon the fission product yield curve, where this was the yield and this was the mass number. Remember that? Now this is the parent. These parents, if they're unstable, they're going to decay to a daughter product, probably through beta decay to a fission fragment daughter. So then, for instance, this could be tellurium that decays to iodine. That's not the decay chain we're looking at, though. But this fission product right here decays to a fission product daughter, fission fragment daughter, which then emits a neutron. Versus this, a neutron created directly during the fission event. We know that this occurred very rapidly in terms of time. It was less than 10 to the minus 14th seconds. This decay here, to actually show up, that neutron to show up, on average, it takes about 12.7 seconds to occur. So this is a slowing down process, essentially, of this neutron showing up in our life cycle of neutrons. And I'm getting less of this occurring over core life because plutonium, if I was to interact here with 239, plutonium-239, and a neutron came in, it just gives off its neutrons and doesn't have as much of a delayed neutron fraction. Right, very key. Can't stress it enough. On the bottom of here, you can see the decay chain for both prompt neutrons showing up instantaneously in essentially less than 10 to the minus 14 seconds. But then here you can see a decay chain of a delayed neutron showing up greater than 10 to the minus 14th, and on average about 12.7 seconds during steady state operation. Starting with 10,000 neutrons. The beta of the core at the beginning of core life, it says 0.007. That means 70 out of every 10,000. At the end of core life, it's only 50 out of every 10,000. Why? Because plutonium-239 is building in. So if you were to look at the prompt neutrons that show up rapidly, at the beginning of core life, there's 9,930. The delayed, on average, it says that's wrong. That's not 12 to the minus 7th seconds. That should be 12.7 seconds on average. But the real definition of a delayed neutron, recall, is greater than 10 to the minus 14th. We'll fix that. Someone go ahead and put in a report. If I don't do it by next revision, that'll be in. I'll do it myself. 70 out of every 10,000 are delayed. So there's the total 10,000 at the beginning of core life, and only 70 are delayed. At the end of core life, only 50 are delayed. This kind of puts it all together. Average energy level of a prompt neutron is higher than that of a delayed neutron. Very key. So a delayed neutron is born at a lower energy level, but it's key to note they're both born fast. They're both above 0.1 mega electron volts. And then here's the definition of a prompt neutron is less than 10 to the minus 14th. The definition of a delayed is greater than 10 to the minus 14th, and this should be 12.7 seconds on average.